can.
Okay, great. Okay, so today our presentation is going to be on fault location, detection, and classification. Just a few things before we get started. This is being recorded and the slides will be made available to you afterwards. To introduce ourselves first, okay, my name is Nurain Arif and I am a consultant at Optimum Solutions. I have studied electrical and biomedical engineering at FITS, and the main areas where I work on is computer vision, software engineering, and I also work on hardware deployment. And I'm going to hand over to Enzo to introduce himself.
Thanks, Nurain. Hi, everyone. Hope you all are well. My name is Enzo du Plessis. I am a consultant at Optimum Solutions. My background is in mechanical engineering. And over the just over 3 years that I've been at Optimum, I've been exposed to a variety of different projects, whether that's in artificial intelligence and simulation engineering. And as of late, I've been helping out a lot with more of the academic team at different universities as well, incorporating MATLAB, Simulink, and Simscape. Thanks.
Great, thank you. Now we're going to go into a quick introduction about Optimum. So first and foremost, we are a high-tech consulting and engineering firm. The fields we specialize in are creating technical, business, as well as engineering solutions. And this is because we love to make a real-world difference to our clients. So we focus mainly in 3 areas, and I will also delve deeper into the projects we've done into these 3 areas, but they are artificial intelligence, model operations, and simulation engineering. And here are just some highlights about our company. So we've been a trusted partner to MathWorks since 1992. We have also been involved in some of the development of some MathWorks products, and we have delivered more than 250 projects locally as well as some internationally. And we also have a skilled consulting team of more than 30 engineers as well as developers. So this is a slide just to show some of the cool projects we've done in each competency. So within the AI competency, we've been delivering solutions that make use of AI from the very beginning. And some recent work includes computer vision solutions for hazardous environments. For our model operations, this involves building robust operational grade software that impacts operation. And then a recent example we did is we built a custom credit decisioning engine for an African's microfinance provider. And last of all, in the engineered systems, so our tools enable us to model, simulate, and optimize complex systems. So this will actually be shown in the demo and presentation we are doing today. And also, this is just a few of our examples, so we'd be happy to share more relevant case studies based on whatever you're interested in. So our agenda for today, we're going to first work through the problem statement. We'll then give a real world example where this solution we are coming up with today would have been helpful. And then we're going to go into the simulation aspects where we would be injecting faults into a model. And then from that, we would get our data, which we would classify, and it would help us interpret our faults and use this in our solution. And then finally, after this, we'll do questions. Okay, so today our problem statement will be, can we use data-driven techniques to generate a classification algorithm? And this classification algorithm will be used for fault location detection in power systems. And can we do this using only a limited number of voltage and current measurements? So that's our problem statement for today. Before we jump into it, I just want to give a real-world example where this could have been useful. So in 2018, one undetected fault caused one of the deadliest wildfires in California history. So in this wildfire, 85 lives were lost, and it nearly cost them $17 billion in damage. And all this was caused because of a single hook. So what happened with this hook, it was leaning against the tower, and then it produced this massive fire. So what could have happened if we had a detection or classification algorithm in place? It would have shown that there is a high impedance from the ground to the line, and then it would have flagged this. And also us correctly identifying that this is a single line to ground fault would have let us act immediately rather than ride through it, because this could have been distinguished from a transient or a load event. Okay, great. So now we know the real world example where it could be useful, and it could be used to prevent similar situations like this. Now we're going to jump into the model we will be using today. So over here, we are going to use the IEEE 123 node test feeder. So what this is it's a distribution test system that allows us to evaluate power flow algorithms as well as unbalanced three-phase systems and smart grid operations. But today we're going to be injecting faults into it and using it for this case. So what it consists of are buses, both three-phase, two-phase, as well as single-phase. So the three-phase buses consist of 70 buses, and in each bus we inject 7 fault sequences. The two-phase buses, there's 3 of them, and then we inject 3 fault sequences per bus. And finally, the single-phase bus, there'll be 55 buses, and we inject 1 fault sequence per bus. Right. So and then for this, just to explain to anybody who doesn't know what a bus is and to give an example. So for three-phase buses, these are used in heavy motors in industrial factories. For two-phase buses, this is actually not common within South Africa. So it's mainly in North America, and it's used for stoves and appliances in North America. And then for the single phase bus, it's common in offices and households. And for anybody that does not know what a bus is, so it's sort of a central bar or node, and then it collects electrical power from one or more sources, and then it distributes it to outgoing circuits or loads. Yeah, and I quickly want to show everyone what the circuit looks like. Sorry about that. So this is the circuit over here, and we can see that it is quite a large circuit, so it can be overwhelming if someone has not used Simulink before. And then if we look closely, we can see that there is buses and sources, and it can be overwhelming, but we will break it down in a bit. But before we get to that, I just want to go back to the presentation. And then before we get to that, I just want to explain the faults that we will be going through. Okay, so we have the different types of faults. So over here, we have the first one is the three-phase to ground fault. So we can see all 3 phases are connected to ground, and then this is what causes the fault. And then in the second one, we can see all the 3 phases are connected to each other, and then this is another type of fault. In the third one, we can see that 2 phases are connected to each other. So this is a line-to-line fault. The fourth one is 2 lines connected as well as ground. So this is a double line ground fault. And then finally, we have the last one, which is a single line ground fault. Okay, now I'm going to be switching to Simulink. So a poll is going to show up just to gauge everyone's experience with Simulink. So the poll will show up, and then I'll switch to Simulink to show everyone how we can build a simple circuit before we get into the big circuit. We're first going to build a simple circuit and then inject faults. Great. Okay, so this is the MATLAB interface over here. And what we're going to do is we're going to open a Simulink model. So how we do this is we click new, we click home, then we're going to click Simulink. And then after this, we click Simulink and then we click new model. So I have already opened up a new model over here, and over here we are going to build our model. Okay, so what we have over here is our library browser. And what we do in our library browser is we select the blocks we want to build. So a Simulink is a block interface, and we drag and drop blocks to create multi-domain systems. So over here, we want to create a simple circuit. So these are all the libraries we have available. So what we are interested in is this Simscape library, and particularly in the electrical. So just to show everybody, we click on Simscape, then we click on our electrical. Then it brings up all our blocks. So the first thing we want is a source. So we can see that here we have sources, and then we can see all our different sources. So what we want is our voltage source first of all. And here we have a 3-phase voltage source. Okay, so now we can see we placed our 3-phase voltage source. We also want a fault in our system. So we drag and drop our fault in our system. And then we want a sensor and transducer. So we want our voltage sensor and our current sensor. Here. Sorry, just give me one. Okay, and then we want our voltage sensor. So here's our 3-phase voltage sensor. And we also want our resistors. Here we have our 3-phase resistor. Okay, so we can connect this up. Okay, and besides this library interface, we can also use this to search for blocks we want. So for example, we know in every circuit we need an electrical reference. So then we search for our electrical reference over here, and then we'll put it in our circuit. Great. Okay, and then we also want some measurements. And we want to decide when to inject our fault. So we double click on the blocks to open some options for each of the block. Then, so we want an input to this. So then we allow for an input. Sorry, this is not the input. So an external trigger we want to trigger this fault. And then we allow for that to trigger over here. And then we also want to view our output. So there's 2 ways. So we can use a scope to view it, or we can log our signals to view it. Okay, so for our scope, We want to see our current signal as well as our voltage signal. And then so we need so this is going from the Simscape. So these blocks in the light blue are all Simscape, and you can see this is black because that's Simulink. So there's a converter which we convert the signals. Yeah, and then we connect that over there. Then we need one more of these blocks over here. Then we also connect that to the output. Okay, so then this is our circuit. So we have our resistor, we have our voltage sensor, current sensor, as well as our voltage source and our resistor. And in Simulink, it's very important that we add this block. It's called a solver configuration block. And what it does is it converts all of our blocks into mathematical equations that we can then use. The last thing we need to do is ground our circuit. So over here, we ground our circuit with a grounded neutral. So we need one over here and over here. And then we put a step into our circuit so that at some point we trigger our fault to step into our circuit. Okay, great. So now everything is set up for our circuit. And now we want to observe how the results look. I'm actually just going. Okay. Sorry about that. Then first, so we have our voltage over time and our current over time, and then our scope is our first way to view it. And then we can also, so what they did was log these signals. So it will show in this data inspector. So we run our model and see how the results form. So now the model is running. Great. So now we can look at the results. Okay, so here we can see exactly when the fault went on. So right here at 0.05 seconds, we can see our voltage got way smaller and our current got massively larger. It increased by a lot. And to see how much our original current was, we can just zoom in here quickly. So our original current was between around 20 to minus 20. And then it got much bigger where it went to that. And this makes sense because when we have a fault, it's basically very low resistance, which increases our current by a lot and at the same time decreases our voltage. Okay, so then this was just a simple circuit to show how we can inject faults simply before we move on to the main circuit. And also a poll is just going to appear just to find out if anybody's interested in simulating or building their own circuits. Okay, great. So now we get into the main circuit that we're going to be going through that I showed to everyone earlier. So this circuit we actually run within MATLAB. So this is called a live script. So it's very nice because you can put your documentation as well as your actual code within it. And we're going to be using the model I showed earlier. So what we do is we inject faults into this model. So we have all these fault sequences that we code and we inject it into the model. So first what we have to do is we compile and build this model. So I've already done this. It does take a bit of time, so I did it beforehand. So we built it, and as you can see, our model is built over here within the script. And then we define all our faults. So as I mentioned earlier, there's the line to ground. As we can see, this A, G, B, G, and C, G are all line to ground faults. And then this A, B, G is 2 lines to ground, as well as all of these are 2 lines to ground. And then all of these are all 3 of the lines to ground. So here we define all our fault sequences. You can see over here our 3-phase, 2-phase, as well as single phase. And then finally, we simulate all these fault sequences. So what we are doing, if I can just show you the top level model again. So over here, what we're doing is, if we just go one up, we have all our fault sequences, and then we are, this is from a workspace block. So we did our code in MATLAB, we ran our code, it's stored in our workspace, and then from here, we put it into our Simulink model. We simulate through this whole big IEEE 123 test feeder, and then we get our measurements out. And from this measurements, we create a table, and then this table shows us our voltage as well as our current measurements. And then from this, then we use this to classify, and then Enzo is going to go into a bit more detail about the classification, and I'm going to hand over to him now.
Thanks so much, Nureen. So yeah, just to kind of like provide a bit of a picture of the data that Nureen goes ahead and collects. So from the Simulink model that you've seen, as she injected the faults within the 123 the node feeder power grid, you would go ahead and record data, and that data that then gets sent to MATLAB. And what we're going to be looking at now in terms of the classification is we're going to take one specific bus, this being bus 13, and then we'll be running the simulation. So you would have also seen that you run the simulation about 12 times. And then what this does is with all the results, you basically just concatenate that into a table. And then that table is what we're going to use to go ahead and train our predictive maintenance model, as well as use that to classify that specific model on data that it hasn't seen. So that was just to set the scene. I'm just going to quickly share my screen and the slides. A sec. Okay. Nureen, can you see my screen?
Yes, I can.
Awesome, thanks. Okay, so in terms of the classification algorithm, and this is essentially just building on top of what Nureen has shared, why is it important in a situation like this? Well, there's quite a few reasons why this may be important, but essentially for being able to identify faults and go ahead and classify them, you also have an equipment lifecycle benefit to this, because essentially you will be able to assess the working condition of the specific machinery that you're looking to measure, and also to estimate a likely occurrence of when this specific piece of machinery were to fail. So in predictive maintenance, what we do is we essentially place sensors on the specific machine and record lots of data on it. And this can be massive data sets. And then what we would do is build predictive maintenance models that will then be able to correctly, or to a certain level of accuracy, predict what's called the remaining useful life of that specific machine. And then we'll go ahead and schedule a specific instance where that machine will undergo maintenance, rather than like a service interval, for example, like every year or every 2 years, especially if the machine, especially if if that specific machinery is still good to go for quite some time. The other thing with being able to run the classification algorithm is that it could potentially save lives, surrounding areas, and human and animal lives, as alluded to earlier with the California wildfires. So say, for example, the specific power system or substation was located in a specific area where there might have been some people around, or things like that. Maybe that specific line, had some led into like a bit of a almost like a bush situation where there's a lot of grass, or maybe there's a puddle and that specific line lands in the puddle. Very, very dangerous if you were to step into it and so on. So being able to kind of like identify where this fault occurred, and so essentially where it occurred and what type of fault it is quite invaluable. So the approach that we'll be taking, we'll be going through three main things that kind of like build towards developing the predictive maintenance algorithm. The first thing that we'll be doing, thankfully Nurain has already done that first, we'll be going ahead and collecting data. So for this specific instance, we'll be looking at bus 13, and we'll be essentially partitioning our table with voltage and current readings based on the 12 simulations that we run. And as mentioned, this will be packaged into a table. In this specific instance, the table's row size is 6,660, and the columns are 13. So yeah, and then just moving on, what we'll then be doing is going ahead and preparing the data. So what we'll be doing is selecting unique fault categories. So instead of all of the faults that might have been collected within the table, we'll just be selecting quite a few of them, and then going ahead and training our predictive maintenance model on those specific faults, and then supplying it with a test data set that the model hasn't seen, but still has the same classes of faults that the model was originally trained on. So that's incredibly important, because you wouldn't want to have your model be able to label data that it hasn't necessarily been trained on, because it's not going to be able to do that. So, and then from that data preparation, we're going to go ahead and create a new table, which we'll then use for training. And then what we'll be doing is using the classification learner app within MATLAB. With this specific app, you do need the statistics and machine learning toolbox. And what we'll be doing is we're going to be loading in the table and then also setting aside a test data set, and then training the data that we have collected on some available models that we have. Okay, so as I move over to MATLAB, a poll will be coming up just asking you what level of experience you have with essentially building artificial intelligence / machine learning models. Just please indicate in the chat. Okay. Just give everyone like 10 seconds to just quickly select. Okay, thanks so much. Moving over to MATLAB. So as mentioned, we would have run the simulation 12 times and gone ahead and collected data that we packaged into a table. In this case, we've got a variable named T, which will then give us the voltages and current measurements of that specific bus that we'll go ahead and train our model on. In this specific instance, we can use one bus rather than data from all of the available buses. And the reason for this is because the data that we collect from that specific bus, in this case, bus 13, there could be a fault that occurs elsewhere within the power grid that is essentially locked, or rather logged, based on that specific data's output at bus 13. So if I, just to kind of like show you, I'm going to go to the variable name, which is T1. So you'll see all of this data over here is from bus 13. All of this data over here has been recorded for bus 13, but in, for example, this case over here in row 2, that was the data that was recorded for bus 13, but there also was a fault detected at a different point in the power grid system, and you can see that for a large majority of the data that we have collected. So it would be, in this case, it doesn't always, sometimes depending on the complexity of your model as well as the data that you collect, you would need to take that into account in terms of like having a suitable enough data set that will allow your predictive maintenance model to be able to classify faults that happen elsewhere. But in this situation over here, we we are available to do that just by logging the data from one specific bus. Okay, so all of that has been packaged into this table. And now what we'll go ahead and do is just write a little bit of code that will allow us to go ahead and select all of the unique fault classes that occur. And this has been saved in a variable called unique categories. And you'll be able to see that there's 555 different types of faults that happen. So as Nguyen also mentioned, there's line ground faults, but that happens, let's say, for example, at a subsystem within that Simulink model of 102. And then there's another one at a different time happening at 109 and 111 and so on. So what we'll do is from that original data set, just go ahead and collect all the unique categories that we have. And then what we'll do is we're just going to go ahead and build a mini classification model. We're just going to be taking the last 30 categories that are within this table. So we'll just say interested that original table. We'll just go ahead and choose all the 30 or 31 unique categories. And then we'll go ahead and index into our original table and then build another mini table. In this case, this is a table with 372 rows and 13 columns as well. Okay, but all of those 372 rows has then got data from this original, or rather the categories that we're interested in. So that's only about 30 or 31. Now what we'll go ahead and do with this data now loaded, we can then go ahead and open up the classification learner app. There's two main ways that you can do this, either through the application or you can do this programmatically. So I'll show you both ways. So within MATLAB, you will see that there is, in the tool strip, there's an apps tab. And you'll be able, if you click on that drop down over here, you'll be able to see all of the different apps that you have available based on your tool, the toolboxes that you have for that specific MATLAB license. So you can go ahead and scroll. There's MATLAB stuff, machine learning, math, statistics, and optimization, and so on. In this case, we're interested in the classification learner app. You can go ahead and click on it, and it should open a new window. That looks like this. Okay. If you want to do this programmatically, you can just go to the command window and type in classification learner, and that'll go ahead and call the classification learner function, which will then essentially open up that exact same window that looks like this. You don't have to pass any input arguments to it. You also don't have to specify an output argument. So that's just two ways in essentially doing the same thing. So now that we're here, within the classification learner app, we would now like to go ahead and load in the data. So you can click on new session, and there are three main options that you have. You can either load in data from the workspace, from the MATLAB workspace, provided that that data is there. Or what you can do is, if you want to rather browse to a specific location on your computer and go ahead and add the data, you can also do that. Bear in mind, with this option from data file, only specific file formats are supported. For example, Excel spreadsheets, CSV files, and so on. There might be a few more, but just bear in mind that there are like a limited number of file formats supported. The third option, which is actually a new feature within Classification Learner, is you can upload data from a trained model itself if you were interested in doing that. In this case, workspace data will work just fine. So we'll go ahead and open that, and we'll to present you with some inputs. So in this case, we'll click on dataset variable, and our subset data that we're looking to upload is T1. And what it will then do is go ahead and split between the data that you want to train, as well as what the labels are that you want your classification algorithm to go ahead and classify. On the right-hand side, you'll see a validation scheme. This is quite important to use as well, especially if you would like to protect your model from overfitting. So you can either use a cross-validation, a holdout validation, or a resubstitution validation. In this case, cross-validation is fine. If you would like to learn more about the validation schemes and when to use which one, you can just click on the link on Read About Validation. It'll throw up a MathWorks article detailing the different types of validations and when it is advisable to use one or the other. I'm just going to leave the default values here as well. What I also typically like to do is also just set aside some data for testing. And this is essentially data that's not going to be seen by the model in terms of its training. So we'll set aside a data set just for testing. And once the model is done training, we'll go ahead and show it the test data set that it can go ahead and predict. Okay, so I'm just going to set aside 10%, and I'm going to click on Start Session. And now what I can do is, just as a demonstration, I would just like to go ahead and select a specific model. So there are different ones that you can select here as well. Some of them have a more simpler architecture to others. But in this case, we can just click on All Quick to Train, and this is going to give you like a bit of an idea of the accuracy or validation of how these specific quick to train models would perform on the data set that you have. So I'll click on All Quick to Train, and let's go ahead and train those specific models. Okay. There's also, if you guys are more comfortable with programming, you don't have to do this all in the app. You can also follow a more programmatic method to go ahead and essentially do exactly what I'm doing now within this app. I'll also show you what that looks like once we're done. So as the models are training, you'll see some validation scores come in. And as I'm just waiting for the other three to train, but currently we are sitting at a validation score of about 93.8%, which is not bad. But now what we can also go ahead and do, and you can also see the confusion matrix pop up over here. Confusion matrix is just a really nice way to go ahead and evaluate how well your model performed based on what it predicted versus what the actual true specific class was at that specific point. So you'll see for models that perform really, really well, you'll see a diagonal line running from left to right. And some of the cases where it didn't perform as well, you'll see like I'm not sure what color this is, like a light pink or light red type of color pop up. So this is your validation confusion matrix. But now let's go ahead and look at how the model performs under data that it hasn't seen. So what we can do is within the tool strip, there's a test tab over there, and we go ahead and test the model on data that it hasn't seen. We can just click on Test Selected. It's pretty quick, and it gives about an accuracy score of 93.5%. If you would like more details on this, there is a summary page over here that will allow you to see what the validation scores were, what the cost was, how quickly it goes ahead and predicts or makes a prediction. So this, depending on where you want, how quickly you want results for your model. So you can go ahead and also select a model that's kind of like quicker in terms of prediction. And then there's also test results as well. So this goes ahead and tells you what the accuracy was, what the error rate was. There's some other additional parameters that you can also go ahead and set, retrain the model, and then go ahead and test again. Okay. There's also some other types of plots that you can also plot. For example, ROC curve, prediction recall, depending on what you're looking for. Okay, so as I've mentioned, in this case, this is more of like an application-based way of doing it, but you can also do this programmatically. So essentially with these applications, what they have is just the front end where you enter in information and it runs all the code in the back end. If you would like a bit more control in terms of, how your model is being trained, how the test and the trained data sets are split. If you would like to maybe even reproduce the results as well, you can do this programmatically. And the way that you can go ahead and do this is go ahead and select what your unique categories, all the unique categories for the labels, and then select how many of those unique categories you would like your model to be trained on, as well as being able to test. So very similar step to what we did here. We go ahead and index into our original data set, and then create a new table. In this case, it's called data table. Because we're looking at 25 unique categories, this data table is about 312 rows and 13 columns. Okay. Then the reason why I use this RNG function, that's just a random number generator. That allows me to, if I were to go ahead and split my test and my training data set, or rather the data table into a test and a train data set, I can go ahead and run this as many times as I want, but then this would also allow me to then split it in exactly the same way. So there's no randomization in terms of how the train data set is collected in test data sets as well. Okay. And then what you can go ahead and do is go ahead and build a train data set. In this case, it's 250 rows, and also a test data set, which is 62 rows as well. And then you can also go ahead and verify whether each of the data over here has been split into train and test. The way you can do that really is just taking the number of rows here, 250 plus 62, that should add up to 312. And if you look at your table, it should say 312 as well. Okay. And then what you can go ahead and do is go ahead and select a model. So that fit function over there goes ahead and essentially fits your training data to whatever specific model that you're looking for. In this case, we're using a multi-class efficient logistic regression model, which you can use any model of your choosing. What we'll then do is go ahead and predict the test data set based on the model that has been trained, and then give a score, a test accuracy score. And then as an additional measure, if you would like to do so, we can go ahead and also see what the correct predictions were. So in this case, we've got 62 rows, so 62 predictions that we need to do. We can go ahead and run this. And you should see model test accuracy is pretty high, 94.3%. And we also do see that the model predicted 58 fault classes out of 62 correct, which is pretty impressive. Okay, now that you have that, and once that you're comfortable with how different models perform against your specific data set, you can now go ahead and increase the number of categories to something much larger, so that your model is able to classify across a wide range of faults. Okay, so, and then what we'll also go through is some data visualization. So I've already showed the confusion matrix to you, but you can go ahead and also include that programmatically. The function for that is called confusion chart. And we'll go ahead and specify our fault classes as well, original fault classes, as well as the fault classes that the model has predicted. So if you run that, you should see your confusion matrix pop up. These are the ones that got correct, and it got about 4 wrong, which is very consistent with the sign over here being 58 fault classes were predicted correctly out of 62. You can also go ahead and make this a little bit smaller and say we want the last 15 unique categories. Run the model again, and you should see a new model accuracy score, and then how many fault classes the model predicted correctly. Go ahead and run the confusion matrix again, and you'll also be able to see which of the predicted classes it got correct and which ones it did not. If I come back to the slide over here, we've already kind of like discussed the confusion matrix as well as some training and validation metrics. If you would like some more information in terms of how you can display the data that you've collected, how to log it, how to essentially just compile it into a report or export it to an Excel file or whatever the case is, I have included some additional useful links for that as well. There's also this link that I quickly just want to show that goes into how, or rather it's like a MathWorks article on how you can go ahead and design algorithms for condition monitoring and predictive maintenance. Runs through pretty much more or less the same steps that I've already just showed to you. So, for example, acquiring data, going ahead and pre-processing it, identify your condition indicators, as well as going ahead and training the detection or prediction model. And if you are interested, how to go ahead and deploy and integrate that onto like a live site or a server or onto some type of cloud platform. Okay, that is it from both me and Nurain. Are there any questions? We're just going to allow about 7 to 8 minutes of questions, and then we'll go ahead and close off. Yes, Samuel. Michelle, you might just need to unmute the mic, or
yeah, sure, I'll do that now.
Cool.
You should be able to unmute now.
Okay, Samuel, go for it.
Yes, thank you very much for the presentation. I just want to ask, is there a way one can have access to, is there a way someone can have access to these things that you've presented, especially, I noticed so many things were done at the back end, like all the cases, all the scenarios that were run, the labeling that were done, some of these things are not something one is privy to. So to what extent can we have some of the presentation that were made?
Okay. So I have spoken to our internal team. We can make the slides available to you in a PDF format. The model that was shown in like on MATLAB, we believe is also publicly available. So I'll just check back with our internal team, and once we are and once we do have privy to share it, we can do so as well. So I will get back to you on that. Yeah. Sipo.
Good morning, everybody. Thanks very much for the invites. Firstly, for this presentation, very insightful. I'm currently doing some research work on this kind of work, modeling. And I've been experiencing, so I'm using 2026 MATLAB A, so it looks like it's similar to what you're just using. So what I was doing is I'm modeling a 14 bus IEEE C-Gray system. I'm doing reinforcement learning training on it. But now the problem, I'm modeling first, right? So the problem that I'm experiencing, I've completed the model, but when I'm running, like I wanted to do a load flow analysis on it, and I just keep on getting errors, of which I am correcting the errors, but I'm still, example, on one of the buses, I'm getting a 0 voltage, and I think that bus, it's making my whole model not to respond well on the load flow. So I've corrected the parameters. I've put the references. What you call it? You called it what you call
Electrical
this?
references.
Differences, yes. I've done everything, but it's just like even when I'm correcting through the command tab, it's still not. So I just feel like I need like a more knowledgeable person on how to solve this issue, because I think this 2026 is actually different to the 2023 Simulink that I was using before. So some of the things are just a bit tricky from there. So maybe some advice on who can assist me, or I'm even willing to travel to wherever in South Africa for whoever's got a better knowledge on assisting me on this kind of issue that I have.
On your end, you want to answer that? Or
So the process I'm not too sure, but I think at Optimum we could assist you. You could send us Enzo or I an email, and then we can take it from there, and we can discuss further with the errors that you're facing and what the way forward is.
Okay. Okay,
So-
thanks very much for that. Yeah.
So Sipho, if you have, I believe we probably do have your email address. If you have registered for the event, what we can do is get in contact with you and then determine the best course of action in terms of the assistance that you require and so on. That would help.
Okay. I'll just I think the email I was sent by the invite by Michelle. So
Yes, hi Sipho. I will reach out to you after this to set something up with you.
okay, thanks very
Thanks,
much.
Sipho.
See Mukwena, I think you were next.
Okay, thanks guys for the presentation. It was very nice. Maybe I missed it. Can you maybe spend maybe a minute or so going over the data cleaning part?
Yeah, so I quickly, I'm just in the interest of time, I'll quickly just show you how we gone about in doing that. So if you look at this classification algorithm slide, after collecting that specific data, in this case, we didn't have to do much cleaning. There wasn't any missing, values of it. There wasn't any erroneous values. So there wasn't much cleaning that we had to do. Pretty much based also on how you build your Simulink model. You would also kind of specify what data types you are looking for your data and so on. And then in terms of, I think what you mean by the cleaning is how we go ahead and build a subset of that data, which would then go into the predictive maintenance algorithm. Is that maybe what you mean? Or did you actually mean pre-processing and cleaning and stuff?
I think.
Oh no, I meant the pre-processing and also the cleaning, like removing your outliers and that type of cleaning.
Okay. So in this case, we didn't necessarily, do a lot of pre-processing or, removing any outliers in cases like that. But Nureen also did mention in her section, you'll see that when there is a fault, your current shoots up massively and your voltage drops in a sense as well. We would actually want to have that data available so that we're able to go ahead and classify that specific fault. So in cases like this, especially because this is fault detection, you would want that type of outlier data, if you will. But in other cases where you are building models, you might not. So it really does depend on your specific application.
Yeah.
Does that make
Also,
sense?
just to jump in, so also for this, we used to train our model, we use simulated values. So because simulated values generally aren't that messy because we're building what we want to simulate. So if we use, say, real world data that we want to train a model, there would definitely be more need for pre-processing because that's much more messy than simulated data.
Okay, thanks.
Mwamba, I saw your hand up, but I see you put it down again. Did you have another question?
Yes. Oh, thank you. Say, just for the sake of time, I was running. I wanted to leave the meeting, but thank you for your presentation. I just have a question related that after you've done the classification and all those things, I couldn't see a place where you've mentioned the types of fault. I've seen that you've started by collecting all those data and so on. You went through the training and everything, but the types of fault, how are we going to get it? That's the part I could not get it. Thank you.
Okay. So just to quickly summarize, the types of faults are within this original table. So that table T over here, you'll see your fault classes over here. So there's line, ground faults, of a single, two-phase and three-phase, and then also where that specific fault located within the Simulink model. Maybe Nurain would like to, maybe she can add a little bit more about that in terms of that. But yeah, that's where our fault classes come from, if that answers your question.
Yeah, thank you. Thank you.
Okay. Just one more question. Samuel, do you have a follow-up?
Yes, I do. Thank you very much. I was not given an invite to this. I don't know how I registered on time. So I'm wondering, Noreen, is it possible to still have access to you? Because I'm trying to work on certain things and I will need assistance later
What are you
on.
trying to work on?
Building something similar to this, but I'm actually using a real network. I'm trying to build on a real network.
Okay, sure. You can, I can get your email address, then I'll send you an email and
Okay,
then we can have a session.
thank you very much.
Okay. Thanks everyone for the good questions that were asked. Just a last slide and a last poll that comes up. Just to kind of like wrap things up. So if you would like to continue your journey with Optinum, we are also, you'll see a poll come up now. If you would be interested in any additional follow-ups. So there is more of the agentic AI discovery sessions that a lot of the technology companies across the world is essentially pursuing at the moment. And just at a high level, agentic AI is something relatively new. And that allows you to have agents embedded within your workflow, whether that's a Python, C++, or MATLAB in this case, to go ahead and take care of a lot of the specific tasks within your workflow. So this could be building or rather writing MATLAB code, testing it for you, building Simulink models, and things like that, so that you are able, as an engineer or a decision maker, focused on essentially architecture, design patterns, more of the stuff that AI at the moment can't do just yet. So if you are interested in that, please go ahead and indicate on the poll whether you would like to book an agentic AI discovery session with one of our consultants, of which some of them are also in this chat. Then the second thing is, if you are interested in more predictive maintenance type workflows, there is also what we offer from Optinum, a training course called Predictive Maintenance with MATLAB. So this is a 2-day training course. It is CPD accredited as well. So if you are registered as with EXA, you are able to get 2 CPD points as well. And what will go into there is a lot more depth in terms of data pre-processing, cleaning, classification models, analyzing signals, how to go ahead and clean them up, all that type of stuff. So if you are interested, please also do indicate on the poll, and one of us will be in contact with you soon. Okay, and that is everything from us. So thanks very much for attending the webinar. Yeah, and I hope to see you guys hopefully again soon. I see Mukwena, you've got a question, if you maybe just quickly want to ask.
Okay, before you leave, guys, I'm actually a process engineer, but I'm also building models for my work. So do you have any courses for, in particular, process engineers?
Process engineers, maybe let me email you so that I can just kind of like, because process engineering is quite broad. So if you are looking for something a bit more specific, let's maybe just get in contact, and then I can maybe like suggest a next or a recommended next step for you that is more suited to your use case. Okay, awesome. Right. Thanks so much, everyone. Thanks so much for making the time to attend. I hope the session was informative, and we really appreciate it. Hope to see you guys soon. Sipo, do you have a question? Okay.
Thanks, everyone.
Thanks.